calculating compound interest requires that we use the correct formula for the given situation. We will use the formula on the left for any compounding period that is less than continuous. So our compounding periods of quarterly, monthly, daily, weekly, whatever the amount of time that is decided upon as the compounding period, we'll use the formula on the left. Keep in mind a few things about the formula on the left. As you type this into a calculator, some calculators are not sophisticated enough to deal with this typed in directly. So I would recommend working your way from the inside out as you add in more pieces of the formula. What I mean by that is, I would ask your calculator to first calculate R divided by N. Remember that R is the rate as a decimal, and N is the number of compounding periods in 1 year. Because you are compounding over a period of time that's not a year, weekly, monthly, daily, this fraction serves to split that rate up and have it be calculated that many times. So if you have a rate that's, say, 4% and you're compounding weekly, this fraction takes that 4% and breaks it into 52 equally sized pieces. The next thing you're going to do with that fraction after you've calculated is you should add it to the 1, staying inside of the parentheses. That 1 serves as the growth factor. So when you take that rate and you add it to the 1, you are essentially getting to 100% plus whatever that new percentage is that you're getting from this fraction. After that addition is finished, that's then when you raise it to the power of nt. T, of course, representing the number of years. So look at what that power is actually saying. I want this growth factor that many times. And that many times is, how many times do I compound in a year times the number of years? You could also think of this entire power as the total compounds. If you don't want to use NT or don't want to try to remember NT, you can think of that power needing to be how many total times will it compound over the given time period. When that's all done, then we multiply by the amount of money that we started with. So this is for any of those compounding periods that are not continuous, weekly, daily, quarterly, and so on. In the situation where we have continuous compounding, we have a much simpler formula. The natural base E is what occurs over here when the number of compounding periods is increased without bound. So as you increase the number of compounding periods to the trillionth of a second, the quadrillionth of a second, there is an upper limit on that. And the upper limit is the natural base E. You'll notice in the continuous compounding formula that the rate is now part of the power. That's okay. We don't need the n anymore because we know that it's continuous. There's no changing the decisions based on that number of compounding periods. So we have the r up here with the t. They become the exponent of the e. And we multiply again by the original principal. So let's try a few of these. Let's look at this example where we have a principal of $6,000, a rate of 4%. We're going to do this over a 6-year period. Let's begin by comparing, daily compounding with weekly compounding. So let's start with the daily compounding. With daily compounding, we have the $6,000 principal, 1 plus the 4%, broken into 360 subsections for the 360 compounds that will happen. And in the power, we have 360 times 6. That's serving as the total number of compounds over that 6-year period. Careful with your typing and your evaluation, and you can check me on this, but you should get 762739. Let's compare that to weekly compounding. Weekly compounding is going to look very similar, obviously with just the difference of the number of compounding periods. And in our power, we're now going to have 52 times 6 as the total number of compounding periods. That's less compounds than we had with daily compounding, which means we should expect our final amount to be less than the daily compounding amount, which it is. That's not an accident. That will happen no matter what. Now let's look at the exact same setup, but this time sent through the lens of continuous compounding. Here's our continuous compounding formula. We have a principal of 6,000, a rate of 4% over a 6-year period. We should anticipate, as continuous compounding is constantly adding that interest in and getting new interest on top of that, we should expect this to be the largest of the 3 results that we have for this setup, and it most certainly is. Is it the most by a lot? No. It only surpasses daily compounding, the amount we got here, by 10 cents, but it is still the largest of the 3 of them. That relationship between this formula and this formula, namely that E, that number E, that approximation of 2.718, that E as the upper bound of that growth factor when it's raised to increasingly large powers. That relationship allows us to use this formula for the scenario of continuous compounding.